So in our last lesson we learned all about what an exponential function is, how they are something that involves a constant for a base and a variable for an exponent. So today we are going to look at how four specific parameters that we have looked at before in other types of functions, a, b, h, and k, how those four parameters will affect the graphs of exponential functions. So let's go ahead and get started. Now, on your handout, you have the following function written out with all of the transformation parameters, a, b, h, and k. So the effects of these parameters, h and k, will be explored first. So I've asked you to graph these all on Desmos, I guess, and we're going to take a look at how each of these graphs will look after the transformation has been applied. So we're going to start with a basic function, which is essentially y equals c to the x. So c is the constant 3, x is the variable in the exponent here. This would be the parameter k. As you can see, k is the additive factor at the end of the formula. So take a look at these three graphs on Desmos and see how they are affecting the function. So we start with our base function, y equals 3 to the power of x, and notice that we have our regular y-intercept, where x is 0 and y is 1. Now, if we apply this k parameter, you can see what the graph of this one will look like. Now, we have taken and added a +2 as our k parameter, and if you look at the y-intercept in our new graph, it has been shifted up from 1 to 3, which is a vertical shift of +2. So let's take a look at this one, 3 to the x minus 4. You can probably make predictions as to what's going to happen here with our y-intercept. It will be a vertical shift of -4, meaning it will go from 1 to what? You guessed it, -3. So take your y value, subtract the value of the k, or I guess add the value of the k. So in the first one we added 2, in the second one we added a -4, which brought us down to our new y-intercept of -3. So that is the effect of k on the graph of an exponential function. So compare the graphs in set A for any constant k. Describe the relationship between the graphs of y equals 3x, 3 to the x, and y equals 3 to the x plus k. I guess you could just write something simple here, such as k causes a vertical shift of k units. Alright, so that's k. Fairly straightforward. It does the same thing as the k we've looked at in every other function that we have transformed this year. Now let's take a look at the effect of h. This one's a little different from something we've seen in the past because it's contained in an exponent. So let's find out what happens. So we're going to take a look at these three functions. So again, we're starting with a regular y equals c constant to the power of x variable, and we're applying a certain shift. So start with y equals 2 to the power of x, and we have our regular y-intercept of 0 and 1. And let's see what happens when we make an h value of 1. Now be careful, the h value here is not -1, it's +1, because in the formula it says x minus h. So whatever comes after the minus, that's our h value, and here it is +1. So We could look at the y-intercept here, but I don't think it's really going to tell us a whole lot about what's actually going on with this graph. But if we take and we drew a horizontal line, let me just do that. I never thought to do this ahead of time, so y equals 1. So follow this line, y equals 1, and figure out what the x value is. So in our original function, where we had no h, our x value is 0. In our new function, where we have an h of positive 1, our x value is positive 1, where the y value remains the same as it was in the other one. So let's take a look at this one, x plus 1. Now, was that the one I actually had written down? Yeah, I did. Oh, I had x minus 3. We can take a look at that too if we want. Y equals 2 to the x plus 1. Now here, the h value would actually be negative 1 because in our formula it's x minus h. So to turn a minus into a plus, h must be a negative. So let's see what happens with this one when we graph it. I'll get rid of that other one. And you notice that we have now this value where our x value, instead of 0, where y is 1, our x value is negative 1. So it's been shifted 1 unit to the left. So here we shifted 1 unit to the right, and down here we shifted 1 unit to the left. So this ends up actually being very similar to the other h values we've looked at for other types of functions throughout this course, where h represents a horizontal shift. And a positive h means a shift to the right, and a negative h means a shift to the left. So if we just change this to a 3, like I had in the handout, you'll notice now that this has been shifted to the right by 3 units. Okay? So quickly go down and fill in what h does. For any constant h, describe the relationship between the graphs of 2 to the x and 2 to the x minus h. And we can just say there is a horizontal shift of h units. Done. Describe the roles of the parameters h and k in the functions of the form y equals all this junk. Okay, and we've done that right here. K causes a vertical shift, h causes a horizontal shift. Now, one more thing to note about the vertical shift that I should have pointed out before. Let's just go back and take a look. Now normally with our y equals c to the x function, we have a horizontal asymptote at 0. So it will never cross that 0 line. But now if we do a vertical shift of +2, you'll notice that we don't ever go down below the value of 2. So we have shifted our horizontal asymptote up 2 units. And that's consistent with the vertical shift of the entire graph. So we shift not only every point along the graph, but also the horizontal asymptote. Alright, moving on. Now we want to look at the effects of the parameters a and b. So let's start with a, where a is a multiplicative factor in front of your original constant base, c. So let's take a look at how this will affect our graphs. So we start with just a regular decay function, y equals 1/2 to the power of x. So c, our constant here, is 1/2. Now let's take a look at what happens when we apply a multiplicative factor of 3 and take a look at some key points. So now we have essentially multiplied our y value by that multiplicative factor. In this case, that is 3. So instead of the intercept 0 and 1, we now have the intercept 0 and 3. So let's see what happens with a negative 4. So here, when we have a negative a value, in previous types of functions, a negative a value has always been a reflection of some kind. So let's see if that remains consistent with these ones. And we find out that it does. So we have taken this graph and we have reflected it in the x-axis, and not only that, but since it's 4, we have applied a multiplicative stretch factor of 4 units. So instead of 0 and 1, we now have 0 and negative 4. So basically you can just take your regular y value that would occur anywhere on your graph and multiply that y value by the a value, the multiplicative stretch factor, and you will get the new y value. Alright, so let's take a look at what a fractional value will do to this thing. And again, 3/4, it makes this thing a little less steep, and you find out that 0.75, yeah, that's the same as 3/4, so we have applied basically a little bit of sort of a compression here. And that is basically all we need to know about the a value. So we can always find our mapping goes from x and the point y to x and our new point a times y. Alright, so let's take a look at the parameter b. This is our final parameter, and it is found as a multiplicative factor on the exponent. So here we'll start with our base function, y equals 2 to the power of x, and I gotta get rid of that one that I forgot to take off. Okay, so 2 to the power of x. Now, when we apply a multiplicative factor to the exponent, let's see how this affects the graph. Now you notice that we have the exact same y-intercept as before, so we haven't really moved this thing or applied kind of a shift on it, any of the resulting values, the y values. But if you take a look at some other points, such as where x equals 1, and maybe I'll just punch that in here so we can see it a little clearer. So where x equals 1, oh yeah, I gotta make it show up. Okay, so where x equals 1. Now, in our original graph, not gonna let me plot that point. Hey, Desmos? Jerk. Okay, where x equals 1, y equals 2. Now, if we follow that x equals 1 line, where x equals 1, y now equals 8. So essentially, we could map this thing by taking our regular point, x and y, and mapping it now to x and y to the power of the absolute value of that b. So where b was 3, we went from 1 and 2 to 1 and 2 to the power of 3, which ended up being 1 and 8, which we know 8 is 2 cubed. So if you can predict what's going to happen here, 2 to the power of 1/3, now we would normally have the point 1 and 2 for this with a base of 2. Here we should have 1 and 2 to the 1/3. Now this one's going to be a little trickier for us because anything to a rational power is actually a root, and this would be the cubed root of 2, which is going to be a little more difficult to calculate. So let's not use that one as our example. Let's take a look at the next one, the negative 2. 2 to the power of negative 2x. So normally, again, we'd have 1 and 2. 2 to the power of 1 would be 2. Now we have 2 to the power of negative 2 times 1. So instead, we should be able to say we will have the point 1 and y to the absolute value of this thing right here, this b value, which here is negative 2. Now the absolute value of negative 2 is 2, so this should be our regular y, which is 2, but now to the power of positive 2, which should give us 4, right? So let's go see if that holds true. It's 2 to the power of negative 2x. Now we'll also see what the effect of a negative coefficient in front of the exponent does, and you see that it also causes a reflection, and this reflection is about the y-axis, so it's reflected from side to side. Of course, we also applied a stretch, so it's not a perfect reflection in this case, but if we took away that 2, you see now that it is a perfect reflection. Whoa, what are you doing to me here? Oh, you're killing me. Okay, so now you see that it would be a perfect reflection. But let's put that 2 back and see what we've got going on here. So we basically we wanted to see if we had the point 1 and 4. So let's find where x equals, negative 1 and 4, because now our x value has been turned into a negative. So let's see if that's true, and we find the point negative 1 and 4 right there. So we can take our y value and raise it to the absolute value of the power of, or the absolute value of the b parameter. So we don't have the point 1 and 4, we have the point negative 1 and 4 because we have applied the negative shift, or the negative factor, to the x value. Again, this one would be very tricky to figure out because this is a rational exponent, and we would end up with the cubed root of x to actually the square root of x cubed, which would not be a lot of fun to do. But did I graph that? I tried another one here, multiplicative factor. You'll notice that the rational coefficients, or the rational b values, where we have a fraction, causes the slope to be much less steep. So instead of 2 to the x, which is a regular curve, if we have a whole number coefficient, or whole number b value, this graph gets very steep. And the larger this multiplicative b value, the steeper that graph will be. So you can see if... Yep, go ahead. Anytime now. Okay. Now you can see that that thing gets really steep really fast. And if we change it to a ratio or a fraction, you can see that it doesn't get steep very fast. It stays very gradual as your curve here. So that is the effect of the 4 parameters, and I'm going to leave it to you to go down and answer these questions there based on what you just saw. And I don't know why it says H and K again. Maybe that was just a reminder. This should be A and B. Oops. Typical. Okay, so this is your summary. You can pause this and fill this in if I go a little too fast for you. The A parameter is a vertical stretch about the x-axis. So it stretches up and down this way. I know it seems weird because this is the y-axis, but it's a stretch about the x-axis, meaning it stretches that way. It stretches by a factor of a, and if a is less than 0, so if a is negative, then it's a reflection about the x-axis, so it goes from this down to that. And you can see the mapping notation is fairly simple. Instead of x and y, we now have x and a times y. B, the horizontal stretch about the y-axis, so it's a stretch this way, and it stretches by a factor of 1 over the absolute value of b. If b is less than 0, reflection in the y-axis, so it flips from this way to that way, as we saw, and this should have a negative here. So you could change the x value to a negative and then find the new value. This is if b is less than 0, then you will have the negative right there. K is vertical translation of k units. Fairly simple. X and y becomes x and y plus k. H, horizontal translation of h units. So instead of x and y, we have x plus h and y. And then it's important to note that when we are applying these transformations, we should always apply a and b first, the multiplicative factors, so those are the stretches, and then apply the shifts last. It doesn't matter which order a and b come in. It can go a, b, or b, then a. And it doesn't matter which order h and k come in. It could go h, k, and then, or k, then h, as long as these ones come first and these ones come second. And I didn't realize that looked kind of like a smiley face. Alright. Here is an example. And actually I wanted to skip this. I wanted to do the your turn here. Transform the graph of y equals 4 to the x to sketch the graph of y equals 4 to the negative 2 times x plus 5 minus 3. So let's figure out what our parameters are here. And we'll start by making a table that gives us a few points for each of these graphs. So let's do this for the original, y equals 4 to the x. So we would normally have where x equals 1, y equals 4, x equals 2, y equals 4 to the 2, 4 squared is 16, x equals 3, y equals 64. Now let's see what kinds of things we're going to have for this one. Now where x equals 1, we are going to apply a whole bunch of shifts here. So this is your multiplicative factor in your exponent. So that would be your b value. So we have a b value of minus 2. Now we know from our table back here that a b value makes our y value jump significantly, and if it's a negative b value, then we flip because we have a reflection. So if we just applied our b value, we would now have the point negative 1, and instead of 4 to the 1, we would have 4 to the 2. So this would be negative 1 and 16. Maybe I should do this in a different color. From now on, I'll do this one in green. Okay, but that's only if we applied the b value. So we also have some other values. We have an h value. Now this says plus 5. In our formula, it's x minus h. So our h value is actually minus 5. So let's go back and take a look at what our h value does. H is a horizontal translation of h units. So if we have minus 5, we are translating negative 5, which is 5 to the left. So instead of negative 1, we move 5 more to the left, and we get negative 6. So that would be negative 6 and 16. Finally, let's take a look at our last translation. which is minus 3 at the very end. So this is a k value, and this is a vertical translation. So k equals minus 3. So this is 3 down, so this affects our y value. So instead of 16, our y value will be 3 lower than that, which would put us at 13. So 1 and 4 becomes negative 6 and 13. So let's go take a look and see if we are right. Y equals 4 to the x. Let's just modify ones that we already have. Y equals 4 to the x. And then y equals 4 to the minus 2 times x plus 5, x, let's try plus 5, and then minus 3. So let's see if we get the points we expected. We had the point 1 and 4 in our table, and we thought that that would then become, based on all of our translations, the point negative 6 and 13. So let's see if we have that point negative 6 and 13. So I'm just going to quickly type in y equals 13 to see if we can lock it on negative 6. Oh, let's not zoom. Okay. So y equals 13. And sure enough, we have the point negative 6 and 13. Now, because we had h and k both changing in this one, the effect on our y-intercept is a little more complicated than just a straight vertical drop of minus 3, because we would drop minus 3, but then we would also have a horizontal shift of minus 5, so we would drop to minus 2 and then shift way over to the left, and then there's also a stretch factored in there. So it's a little more difficult to find this with multiple parameters involved at the same time. So those are what the graphs look like there, and just draw random lines all over your page and call it a day. So this is the stuff that we had figured out on our own. I didn't mention that a equals 1. We didn't notice that there was anything in front of the original 4, so it was just assumed that that wasn't going to have any effect. And you'll notice that we got all the other 3 right. And these are the graphs of those 2 functions as I just showed you on Desmos. So there you go. Now, a second example, which involves a real life practical problem. It says the radioactive element americium is used in household smoke detectors. Americium-241 has a half-life of approximately 432 years. Let's keep this number in mind. It's going to become important, as well as these words, half-life. The half-life of something, I know you've all taken chemistry, is the amount of time it takes for the sample to reduce to half of its mass. So if we start with 200 micrograms, after 432 years, we are going to be at 100 micrograms. So let's try to figure out how we can figure this out. What is the transformed exponential function that models the graph showing the radioactive decay of 200 micrograms of americium-241? So let's start with our base. Now, we normally have a function that looks something like this, y equals c to the power of x. What is our base? So basically, we know that this is a decay function, so we are going to have a fractional base, because a whole number base creates a growth function that curves like that. We also notice that we have a horizontal asymptote of 0. So there is not going to be a vertical shift factor applied to this graph. So there will be no k. So I'm going to note right away that k equals 0. So what is our base? C. Now the fact that this is called a half-life means we will be reducing the population of the americium atoms to 1/2 of its original mass. So it will be 1/2 as our base. So instead of y, let's just say m for the mass remaining of americium. Now we also know that at a time of 0, so I guess this is t, at 0 years we are going to have a mass of 200 micrograms. After 432 years we are going to have a mass of 100. So if the half-life, let's say, just as a thought experiment, if the half-life was 1 year, then every year this mass would reduce by half. And we could just stick with a simple t, because if t was 1, then we would have half to the power of 1, which would be 1/2, times the original sample size. But since t is 432 years, it does not decay that quickly, and we divide our time in years by 432 in order to show that it will reach half of its original mass after a time of 432 years has gone by. Now, we said that k is 0, so there won't be a shift here, and our b ends up being 1/432. Now, we can see that this is not just the regular y-intercept that we usually have. Most, or any regular y equals c to the x graph would have a y-intercept, we know, of 0 and 1. And this one has a y-intercept of 0 and 200. So you can see that that 1 has become a 200 instead. So we have a multiplicative factor of 200. Now this makes sense because we're not starting with 1 microgram of americium, we're starting with 200 micrograms. So A ends up being 200, the multiplicative factor, and this represents the half-life. So after t divided by 432 years, we will have 200 grams turn into half of that, which is 100 grams. So that makes sense that after 432 years, our 200 grams will have become half of its original sample size. So identify how each of the parameters of the function relates to the transformed graph. Well, we know this already. 200 is a stretch factor, a vertical stretch factor, a stretch about the x-axis, so we're stretching this way. So it stretches from 0 and 1 to 0 and 200. Our b parameter, 432, makes this thing decay a lot more slowly than it otherwise would. If it was just t, it would be decaying every day, and this curve would go, or every year, sorry, and this curve would be very, very steep, and it would reach almost zero mass way, way earlier somewhere over here. Instead of way up here, you can see well past 2,700 years, it starts getting closer and closer and closer to zero. Oops, did it again. I wasn't trying to sound like Britney Spears there, by the way. Terrible song. Should not really be quoting things that I despise. Anyway, so check our answers here. 200 times 1/2 to the t over 432. Yep, that's what we ended up with. And you can see we described a vertical stretch by 430 or by 200, and a horizontal stretch by a factor of 1 over b. So the b value is 1 over 432. 1 divided by that would be 432. So it's a horizontal stretch of 432, where instead of coming down very steeply like this, we have stretched this thing out this way to make it come down a lot more slowly. And that's it for this lesson. I hope that was helpful, and I will see you in class tomorrow. Good night.